Good morning, periods 2 and 3. This is Miss G. It is Wednesday, March 18th, and I hope you're doing well. I hope you got to catch the rainbow yesterday. That was a nice way to start the day. So today, I'm going to first talk about some questions that came up that people emailed. I'm going to go over those. Let me see. I'm going to go over page 319, number 17, 27, and 33. But if you got those and you didn't have any problems with those, you can just skip ahead to the notes. Okay, so starting with section 5.1, page 319, number 17. So here's the question. It was to integrate y to the 3 halves, dy. So we add 1 to the 3 halves in the form of 2 over 2 because we want a common denominator. And we get y to the 5 halves. Then we take the coefficient, which we don't see here, but we know it's 1, and we divide it by our new exponent, which is 5 halves, and we get 2/5. So our integral of y to the 3 halves dy is 2/5 y to the 5 halves, and of course we put in plus c. That was the first one. The second one is one of the answers in the back of the book, number 27. It was correct, except that it should have had a plus c at the end. Thank you, Brenna, for catching that. Shout out to Brenna, period 3. The answer should have been 16x to the 6th minus 8x plus c. And then the third question is this one. The integral is number 33. The integral of 2x cubed minus 1 over x cubed. This is where we had multiple terms in the numerator and a single term in the denominator, and we cannot integrate numerator and integrate denominator. That's not the procedure. You need to separate this into 2 fractions, and I should have actually done that like this so I can show you now. Oops. All right, so here it is. 2x cubed over x cubed minus 1 over x cubed. There we go. And that's what we get. 2x cubed over x cubed minus 1 over x cubed dx. And that's just the rewrite. And then there's more rewrite because we can reduce the x cubes and we get 2 minus, and then we wanted to write this as a power of x, so that's x to the negative 3 power. So we haven't integrated a thing yet. All we did was do a rewrite. Now we're going to integrate. So 2 is really the same as 2x to the 0. So we're going to add 1 to the exponent and divide the current now coefficient 2 by the new exponent, which is 0 plus 1, which is dividing it by 1. So, of course, you don't have to do all this. If you've got it in your head now that the integral of 2 is just going to be 2x. That's fine. Then integrating x to the negative 3, we add 1 to the exponent, divide the coefficient, which actually is a negative 1 here, by the new exponent, which will be negative 2. And then we get plus negative divided by negative plus 1/2 x to our new power of negative 2. And we throw in our plus c. So that answer is correct. But if it didn't match the back of the book, they might have taken the x to the negative 2 power and written it as 1 over x squared. Because remember, negative exponents put this x value, this x variable in the denominator. And then your answer would look like this. 2x plus 1 over 2x squared plus c. Honestly, I would take either this one or this one. Okay, so those are the 3 we wanted to go over. Let's see what is next. Okay, now we have the notes in the lesson for today, which is a continuation of the same section, 5.1, and today we're going to solve differential equations. And what is a differential equation? Let's check out the definition. Differential equation in x and y is an equation that involves x, y, and derivatives of y. That's what makes it a differential equation, the derivatives. To solve a differential equation involves integrating, which you now know how to do. So let's begin. This is from page 316 in your book. There's an example there, and I'm actually going to do the example for you or walk you through it. So they give you the derivative. And so we know this is a differential equation because it has a derivative in it, capital F prime of x, and that's equal to 2x minus 2. The other thing that's different from yesterday is this is an equation. It has an equal sign, and yesterday we just had expressions. integral expressions, we had no equal signs. So we have a derivative, we have an equal sign, we have a differential equation. Solving it means we have to figure out what the original function was. We've got f prime, and we want the original function. And when you integrated yesterday, you really were saying that, for example, let's just look at one of those problems. When we integrated this problem here, we're really saying that y to the 3 halves is the derivative of some function, and that function is 2/5 y to the 5 halves. So we're essentially doing the same thing we did yesterday, but only in the form of an equation. All right, so let's see what we do. So we know that we want to solve and get f of x, capital F of x, the original function. We want to go from f prime to f of x. So we're going to integrate the 2x minus 2 with respect to x. So we have our integral sign and our dx. All right, so we do what you learned yesterday. We add 1 to the exponent. I didn't do it all out for you because I think you can probably do this part in your head now. You add 1 to the exponent. What is the exponent here to begin with? It's x to the first power. You add 1 to it, you get x squared. You divide the current coefficient 2 by the new exponent 2, and your coefficient here becomes a 1. So that's why you don't see it. All right, and then we integrate the minus 2. And we just saw that when you integrate a constant, you get the constant times x. So that's negative 2x. And we throw in our plus c. So what we're doing is we're finding the original function, and that is called a general solution. Now, why is that called a general solution? Because what we have here is a second degree equation. That second degree equation comes up forever and ever in mathematics, right? It's a parabola. So we have the c value, which can be any constant we want. Because when we take the derivative of a constant, like if we make that a 5, we know that if we check this problem, that 5 is going to go to 0. The x squared will become 2x, and the negative 2x will become 2. That's if we took the derivative of this and we got this back. So if we can put anything in here, let's graph this and see. Let's make c be, I don't know, -1, +1, 3, 5. So I put it in my calculator and I'll show you. This is the general solution of a family parabolas. And this is what it's going to look like. Let's see if I can get this going here. I don't know. You're going to be able to see it. All right. So if I hit y equals, how about on first? All right. So y equals, I put in all these equations. They're all the same equation except the c value is 1 here, 3 here, 5 here, -1, -3, and -5. So now what I'm going to do is hit graph and see what happens. We're going to graph them all. What we have is that we hope we have a family of curves. There's one parabola. And let's see, more parabolas. And all that plus c does is shift the same parabola up or down. So we get a whole family. So we get a, and I could go on with this forever. I think I even snuck another one in there somewhere. Now that is the general solution because it refers to all of those parabolas. The c value does. But now let's suppose I want just one of these. I don't want all of them. Well, then I have to give you a point on one of them so that you can figure out what the c value is for that particular one. All right, so now let me remove this and see what's happening here. To single out one, you have to be given a point that's on the one you want, the parabola. So let's say capital F of 1 is 2. Now, what does that mean? That means our x value, this is our x value, this is our y value. So we have the point 1, 2. That's really what this is, the point 1, 2, 1, 2. So x is a 1, y is the 2, and that point's on the graph. So we take our general solution, which is f of x equals x squared minus 2x plus c, and we plug in the 2 for a y. Well, we know that f of x can be written as y equals, so, and we have the rest of our general solution. We plug the 2 in for y and the 1 in for x, and we work it out. And I'm sure you can see that what I end up with here is, it comes up here, 2 equals -1 plus c equals 3. So now all I do is take the general solution, copy the whole thing over, and then just put 3 in where there was a c. And now what I've done is I've singled out one of these. And which one is it? The one I'm not going to erase them all. I could. But I singled out x squared minus 2x plus 3. And that's the one that should be shifted up 3. 1, 2, 3. It's one of these in here. Okay? But that's a particular solution because it singles out one of the graphs, not all of them. Particular solution, it's a parabola passing through 1, 2. All right, let's see. So I'll do one more of these so you can see. So this is from page 320, number 44. We're given a derivative, so we have a differential equation with an equal sign. And we're given what we are calling the initial condition. Our initial condition, I should have said that before, in the last problem, the initial condition was that f of 1 is equal to 2, which is the point 1, 2. Here, it's f of 0 is equal to negative 1. So we're going to find the general solution, then we're going to plug in the point to solve for c to get the particular solution. So first thing I do is I go, I know to get back to the original solution, or the original equation, I have to integrate. So I go from f prime of x to f of x. That's actually integrating that side. And then we're going to integrate 9x squared dx. So we add 1 to the exponent, we get 3. We take the current coefficient divided by the new exponent, we get 9/3. So when we integrate, we get f of x, the original function, equals 3x cubed plus c. That's the general solution. Then you just take the point. That's a family of cubics. Then you just take the point 0, negative 1. And then negative 1 is going to go in for y, substitute in for y, and 0 is going to be substituted in for x. And then we just work that out. I'm sure you can figure that out. And c turns out to be negative 1. Then we just rewrite our general equation, 3x cubed, and then instead of the plus c, we put minus 1. So this is all of these cubics, and this is one particular, hence this is the general solution and this is the particular solution. Okay, I hope you followed that. I've given you only a few to do tonight, page 320, numbers 43, 45, 47, and 49. And, oh, I forgot to check your answers in the back of the book, but please do that. And then if you have any questions, email me, tell me which ones you'd like to see, and I'll be happy to do them tomorrow. So, hope you have a great day, and take care. Thanks. Oh, and shout out to Julia in period 3. All my technology is still working. Thank you.